Good morning. Why don't we go ahead and get started? It is truly my pleasure to introduce our Grand Round speaker this morning, Dr. Jeffrey Silber. Jeff is the Director of Outcomes Research at the Children's Hospital of Philadelphia. He's a professor of pediatrics, anesthesiology, and critical care at the Perelman School of Medicine at Penn, and professor of healthcare management at the Wharton School, again at the University of Pennsylvania. Just by way of a brief biographical background, Dr. Silber founded the Center for Outcomes Research at CHOP with Dr. William Greeley in 1997 and has served as its director since its inception. He's internationally known as an authority on outcomes measurement and the severity adjustment for both adult and pediatric populations. He's published extensively on all aspects of theory of outcome measure, model development, and validation, as well as application of outcome measures to pressing public health issues. Much of his recent work has focused on the use of multivariate matching, which is the topic for his Grand Rounds today, with comparing outcomes specifically with respect to problems in both pediatric and adult medicine, surgery, disparities, and cancer. Dr. Silber's current research interests include the development of new healthcare outcome measures, particularly important in this ACA environment, statistical methodologies in outcomes research, including multivariate matching, clinical economics, measuring healthcare quality, health disparities, and medical decision-making. He's twice been awarded the Article of the Year Award in Health Services Research by the Academy of Health, the leading professional organization concerning health services research in the United States. He earned his MD from Johns Hopkins. He trained with Dr. Batshaw at Johns Hopkins. He went on and got a PhD in healthcare management at the Wharton School of the University of Pennsylvania. He was a Robert Wood Johnson clinical scholar at the University of Pennsylvania, and he was named the first Nancy Abramson Wolfson Endowed Chair in Health Services Research in 2013. So it is truly a pleasure to welcome Dr. Silber to Children's National to give Grand Round's presentation this morning. Jeff?
Is it on now?
Yeah.
Okay. Well, thank you for that nice introduction, and it's been a pleasure to be here. We had a lot of fun last night, and I appreciate your hospitality. It's a real honor to be here. It's actually my first time being here at Children's National, and I'm really enjoying the trip. What I want to do today is talk about some things that I hope most of you will be new to many of you, and I hope most of you won't be too bored with this, but I'll try to make it exciting. It is a statistical talk, so it might be hard to stay with that level of excitement, but hopefully we'll get there. So let me first give you an overview of what I'm going to talk about. I want to talk about how hospitals are usually evaluated, and you all are familiar with rankings and ratings, and I want to get into a little bit of how that's done. And then I want to define indirect standardization, which is the main way that hospitals are evaluated, and it's usually done with regression models. I'm going to go into multivariate matching, define that for you, and then talk about different forms of multivariate matching that we've recently been introducing to the literature, and I'll be describing template matching, hospital-specific template matching, indirect standardization matching, and then finally use these techniques to compare value, which is something that people are interested in nowadays. I'm not a big fan of looking at value. We'll get into that, but I'm going to show you how we would propose to do it, and that work is just about to come out in JAMA Surgery next week. But I think because it's Grand Rounds, I should start with a case presentation. So let me start. Chief complaint, this is the first outcomes crisis for this 150-year-old nationally recognized hospital, presenting with the chief complaint of low rankings on state quality of care reports. History of the present illness. The hospital enjoyed its usual excellent reputation until 2 weeks prior to the consultation, when the state issued its report on hospital quality, ranking all hospitals on rates of complications. Although the hospital had no previous known history of quality problems, the report published in the local morning papers ranked the hospital 30th out of 32 hospitals in the state Adding to the injury was an asterisk, signifying that the hospital was indeed a statistically significant outlier. Over the past 2 weeks since the report was issued, the hospital has experienced loss of patient referrals, decreased insurance contract bonuses, and increased legal complaints. Members of the Board of Trustees, the Chief Quality Officer, and the Physician-in-Chief have developed nausea, vomiting, weight loss, and night sweats. Review of Systems Division Chiefs assure the few who will listen that nothing is wrong with the hospital quality and that these low rankings are simply due to a sicker case mix at their hospital as compared to the 29 other hospitals with better rankings. Outcome statistics have been collected, results are pending, and the plan and hospital course to be discussed. All right, so that's actually a common problem. I've been called into boardrooms when rankings don't look very good for institutions that I am associated with, and it's always interesting to hear the same reply from the clinicians, and that, you know, we have sicker patients. And so the issue of severity adjustment is key, and I don't have to tell you here, you're all very familiar with that. Some hospitals see more difficult patients than other hospitals, and clearly we have to adjust for that if we're going to make sense about giving grades or giving reports, or even just finding out how well we do versus other hospitals to improve the clinical care that we provide. So if severity adjustment is utilized, and if it's going to be done, 99.9% of that adjustment is based on indirect standardization, which is observed over expected. And I would presume that a lot of you have seen some of these kinds of reports. All the report cards are based on it. It's the O over E. So what is indirect standardization? It uses the hospital's own patients and compares their observed outcomes to how the patients were expected to do at the typical hospital. So indirect standardization says, how well do I do on the patients I treat? And compare each hospital indirectly to each other hospital by looking at their O over E. So you look at the O over E, observed over expected for one hospital, compare it to the observed over expected in another. Whoever is doing better, having less observed deaths, for example, than expected, is the better hospital. That's indirect standardization, and almost everyone uses that. Direct standardization asks a slightly different question. It asks how a hospital performs on a mix of patients defined from an outside source. How do I, on a defined set of patients, do compared to all the other hospitals evaluated on the same defined set of patients? So you can compare hospitals directly because they're all being compared with the same exam, the same mix of patients. This is something rarely done, but today with template matching, I'm going to show you how we could do it and how we are doing it with the data available today. So back to indirect standardization. I mentioned observed over expected. There's other ways to do this. You can look at observed minus expected, divide by N, and get differences in outcome rates. The new thing by CMS, by Medicare, is to use a Bayesian stabilized observed over expected called predicted over expected. And that's something that a lot of people are switching to. I think it's a huge mistake, and that's a time for another lecture. But CMS, the Society for Thoracic Surgeons, U.S. News, Consumer Reports, a lot of these have, I think, been infected by this approach, but it's another form of indirect standardization. So in its simplest form, the observed over expected framework needs to count the number of outcomes, say deaths, and compare it to the expected number of outcomes, and it's done with a regression model. So this is the only equation I'll show today, but let me just run through it for a second. What we have here is some outcome Y, and we're going to try to run a regression with some variables. This could be white, if we're looking at, say, outcome in leukemia, this might be white count as X1 and age and other biological variables. But in any event, we can try to estimate how a patient should do. We will usually do it with what's called logistic regression modeling. So we'll estimate the log of the probability of the outcome over 1 minus the probability of the outcome, and it's going to be a function of these clinical variables. This is the typical framework. In fact, And what we do to get O over E is that we make an estimate of the probability of dying for every patient at the hospital, and we sum those probabilities up. That gives us what the expected number of deaths would be, and then we look at the observed number of deaths, and that O over E is how most hospitals are ranked. So almost in every ranking process that uses severity adjustment, one will do this kind of thing. You'll put in clinical variables, you'll work out what the estimated risk is for each patient at your hospital, you sum that up, then you count up the number of bad outcomes. That is your O over E. And generally speaking, this is what's done. So what's wrong with that? And the problem, there are a lot of problems now, and people are I think, unhappy with many of the results that come out of these models. And let me give you a few reasons why. The first is that you can have non-overlapping populations. So the model that you get, the O over E, may be equating two hospitals that see very different patients. It could also be that they have subgroups of types of patients within a given disease. So even if you're equating the same disease across hospitals, the patients could be very different. So you can have non-overlapping populations. So what does that mean? So you have an O over E at one hospital and an O over E at another hospital, and one hospital is said to be better because they have few deaths than expected, but the patient populations are very different. So a lot of people say, well, what sense does this make to really say one hospital is better than the other hospital? And so this is probably, this is a problem that a lot of people are paying attention to at the meetings now. How do you make sure that there's overlap in the populations that you're comparing? The second big problem is that the E is often wrong. So we like to think that severity adjustment gets a reasonable E across the hospitals so we can compare the O over E across all the hospitals. But if the E is not formulated right, you can have a lot of bias. So it might be that the model is really not getting the risk of dying correctly or the risk of having a bad outcome correctly, and so that one hospital looks better than the other only because the model is wrong. And then the last point is that the problem with risk adjustment and rating hospitals is that it's all regression coefficients. So what is the chief medical officer or the quality officer really going to do with some beta coefficient that says that they're rated worse than another hospital? So in the end, it's a model that you have to interpret, and you don't really know how to go from the model directly to the patients that are having problems. So with that in mind, what I want to introduce to you today is the use of multivariate matching to look at quality problems. So I want to start by saying, well, what is multivariate matching? When I say matching, most of you think about exact matching. So in exact matching, you'll take a case and you'll match on a few variables, and you'll say, if I have a case and they look similar to the control, and then I can see the reasons for why the case did worse than the control. I say that you can match on a few variables, age, sex, race, few variables, because if you try to match on many variables, you run out of controls in exact matching. So the typical example that we all use is that if you had 20 variables that you wanted to match on, each one had a 50% prevalence and they were independent, you'd need about 1 million controls for every case, and we don't have data sets that are that large. You very quickly run out of controls when you try to exact match. So people have given up on exact matching for the problems that we deal with, where we often have many variables that we want to adjust for and we want to control for. So we've moved into, and people have moved into, multivariate matching. So I'll explain to you what that is. So in multivariate matching, you forego exact matching, and it allows you to control for far more variables, potentially hundreds of patient variables, and you do it because you define a medical distance. And a medical distance is how different one patient is from the other, but not in terms of miles, but in terms of differences across many variables. So it could be differences in white count, it could be differences in age, it could be any kind of risk factor that you're interested in. So you define a medical distance, and it's made up of potentially many variables. And what you want to do is find a case, find a control that has the smallest distance to that case. But that distance now has got to be defined by you, the investigator, with some kind of distance metric that makes sense. And we do this, the skeleton that we do this on, the mathematical structure is called Mahalanobis distance. That's just a geometric function that says one point is a certain distance from another. But the whole trick in multivariate matching with quality is getting the statisticians together with the clinicians and saying, what is a reasonable distance function? So we might not care about hair color, but we might care about white count. And so we have to educate the Mahalanobis distance, this statistical function, to say, these are the important variables, these are the less important variables, and the computer should be searching for controls that are close, have a small distance on the important variables. So we create a Mahalanobis distance, and then there's lots of things that we put into this distance, into the Mahalanobis function. Individual variables that are important, but also risk scores. We could put in multiple risk scores, and we could say to the matching algorithm, you have to be very close on a certain probability of the event, the probability of an infection or probability of death. And if you're not real close, the computer penalizes you and says, you're really far away, and we're going to put a big penalty on finding a control who's not close on risk. We'll find a smaller penalty or no penalty on someone who's very similar on risk. So we'll create a risk score in calipers. Calipers just say you can be above or below the difference. There's also the propensity score. Many people have heard of the propensity score. It's one function out of many that we use. So that says what's the propensity that you actually go to this hospital versus another hospital. It helps balance cases and controls. And then in the end, with all of these functions and individual variables, we get clinicians to educate the distance formula. So in the end, we kind of agree on a distance formula, and then we might go about doing the matching. And we match, but the beautiful thing about matching is that we don't look at outcomes. So we do this whole process without peeking at what actually happened to the patient. We're just interested in what the patient looks like. So we match first, and then we might do this matching process working with clinicians and the statisticians. Together, we might do this for months, matching until we all agree that the patients in the case group look like the control group, but we have no idea how the patients did. The beauty of matching, unlike regression, in regression, you need a Y, you need to run a regression and look at the outcome every time you run your regression. With matching, you keep yourself separate from the outcomes, and you just say, when do I get to the point where my cases look like the controls? At that point, at our lab, we make an announcement, we say we're done, and then we unblind and look at the results. It's an exciting event that occurs once the matching process is over. So there's been a revolution in matching. And as I mentioned, we're using now distance functions rather than exact matching. But there's also a revolution in databases. So we all have the ability now to tap into larger databases with a lot of clinical information, which is great for multivariate matching because you can use all that clinical information to help with making like patients that you want to compare across hospitals, for example. And there are new matching algorithms, and I won't go into that in this talk, but the new algorithms allow you to do this in a speedy fashion and take on bigger problems. And so there's been a great change over the last 10 or 15 years. So what I wanted, that's basically an introduction. So that tells you that there's hospitals that get evaluated using indirect standardization with regression, that there's another technique called matching. And now what I want to do is show you the new work that we've been doing looking at various ways to use matching to evaluate quality. And I'm going to start out by talking about template matching, and then hospital-specific template matching, and then indirect standardization matching. These have both been published in the last few years, and this one has just been accepted and coming out soon. And then another example at the end, if I have time, what I want to do is show you how to look at value with these matching techniques. All right, so this is the first study is on template matching, and it's a form of direct standardization. So it's something seldom done now, but we hope it will be done more often. And the best way to explain template matching is with this figure I found, not with the mathematics. But let's start with this idea that there are individual patients in a database. It could be the FIS database from Children's Hospital Association, or it could be Medicare database, or it could be any system that you have data on. And there are different patients with different types of diseases, and maybe the different sizes of these geometric symbols might reflect various ages, older or younger, or it could be with a worse condition or a better condition. So these geometric symbols are different patients. And what you do as someone who wants to be evaluating quality across hospitals is that you form a template of interesting patients. And you can do it any way you want. It can be a representative template of all the patients that are in your database. It could be a representative set of hard patients or easy patients or patients likely to be seen at your hospital and other hospitals. You make the template, and hopefully you're doing this for a reason that people would agree that they'd want to be judged on that template. You make the template, and here's a representation of the template, and then you use multivariate matching to go to each and every hospital in your system. In this case, we were looking at 217 hospitals in 3 states in the Medicare data set. And these happen to be general surgery and orthopedics patients. We'll get to that. But you will stamp this template out on each of the hospitals. When I say stamp it out, I mean make a copy. Find patients at the hospital that match to the patients in the template. And do this for all the hospitals so that you have copies of the original template at each and every hospital. Now, we find 300 is a good number, so I'm going to use n equals 300 in this example, but we do it with different numbers and different sizes. But so you can imagine each hospital has a copy of the original template, and now we're going to ask which hospitals are doing better or worse on the copied template. The nice thing about a template is that, and if you have it with a large system, is that you have many copies of the same patient throughout the system. So this circle for that patient in the template is going to be copied in this study 216 times between this hospital and the first hospital and 216 other hospitals. But you'll learn a lot about an individual patient because you've got so many duplicates of that patient throughout the health systems that you're studying. And so you can do a lot with these multiple copies. And so to give you an idea, suppose you put together a template. In this case, this is a template of Medicare patients, and they had an average age of 80. They had different kinds of diseases, but we're going to make sure that we've exactly matched for every patient in the template the same procedure in a patient at a hospital across all the hospitals. And then we're going to maybe make sure that the template has if the template has an average age of 80, we would want to make sure that the hospital also has an average age of 80 on their copied template. And we can do this, though, with many, many variables. So where the computational problems come in is in making sure that the average ages are the same across all the hospitals for each and every template, but to do this across all the variables. So there could be 200 variables that we're also matching at the same time. Now, to give you an idea, this is a busy slide, and I want you to concentrate on a few things, so let me set it up for you. To give you an idea of how well this works, this is a data set that had those 217 hospitals, and in that data set, there's a bunch of variables. Now, I'm only listing a few here, and all of the actual procedures are exact match. So all the hospitals' template patients are all exactly the same in terms of their procedures. So there were gallbladders and appendectomies. All of them are exactly the same in terms of the procedure. In terms of variables describing the patients, such as their age and sex and chance of dying based on a complicated risk model or how long the procedure is expected to take, those are all variables we'd like to balance and have good matches on, and comorbidities like heart failure. And so the variables are going down here, and they would go on. And across this direction, we have the distribution of these variables at the hospitals. So this would be the median age, for example, in the middle. This is the lower eighth, the upper eighth, but there'd be a distribution across all the hospitals in terms of age. What we're shooting for is no difference between age across all the hospitals. no difference in terms of the probability of dying on admission for each patient at the hospitals. No difference in the estimated procedure time across the hospitals, so that we know we're fairly comparing the hospitals. And what you look down this column is that there are no differences across all the hospitals, not just from the lower eighth to the upper eighth, but there's no statistical difference in the patient characteristics across the hospitals. And of course, the key is to make sure that you've got the right variables so that everyone agrees that they are comfortable that there are no differences across these hospitals. And so if we then look at outcomes across these hospitals, you'd see something that you haven't seen before. Up to now, you've seen O over E's, and you've seen that some hospitals look better in terms of observed over expected. But very seldom, or now hopefully you'll be looking at these kinds of things in the future, you're going to see how hospitals vary when their templates are the same. So they have the same patients that everyone agrees upon look extremely similar. And yet, let's see if there are differences across the hospitals in terms of, say, mortality. Let's look at 30-day mortality. There we see a statistical difference. There's some problem with mortality. But actually, if you look at everything except for inpatient mortality, which I'm not a big believer in because you have control over when you discharge patients. But if you look at all of the variables that we're looking at here, complications, failure to rescue, readmissions, length of stay, payment, cost, you can see very large differences across the hospitals, yet at the same time, the patients were matched to be extremely similar, such that there were no difference in their variables across these hospitals. Now, you could also look at an individual hospital. So I'm going to say Hospital A, and I'm going to come back to Hospital A throughout the talk. But Hospital A has a set of their 300 patients that's very similar to the rest of the hospitals. Since there's 216 other hospitals and they all had 300 patients, there's 64,000 patients there being controlled to the, being compared to these 300. So Hospital A, in terms of all of its patients, has a very similar age and sex and all the variables. None of these were statistically significant. But what we just try to do in this slide is just to say that the variables were very close. Probability of dying based on a risk model, very similar. Heart failure rates, very similar. So Hospital A is similar to the other 216 hospitals. So how did Hospital A do? And if you look at Hospital A in terms of these variables, what I have here, I'm not going to break out orthopedics and general surgery yet. I'll do that a little bit later with a graph. But Hospital A had an inpatient mortality rate 3.3%. The rest of the hospitals had a 1.7% mortality rate on these matched patients. And then if you look at 30-day mortality, 6% versus 3.2%. So they were the 98th percentile in terms of mortality. So they were not doing so well in terms of mortality. They were doing okay with some things, but we can look at all of their variables because we didn't peek at these outcomes when we did the matches. So now we can look at the outcomes that we were interested in and report that. And what we can see is they're good for some things, not so good for others, but let's concentrate on 30-day mortality, which is kind of the gold standard. You can, as I said, look at Hospital A versus the other 216 hospitals. This is in-hospital mortality. This is a distribution of all the hospitals in terms of their in-hospital mortalities. This is a box plot. This is the upper 95th percentile. So they were almost significant on in-hospital mortality. And then this is 30-day mortality. It doesn't show up very well, but now we can see Hospital A is an outlier. And we can do that for any variable that we're interested in. So you can look at multiple variables when you are comparing this hospital to everyone else. All right, what about a pediatrics example? Because this is a pediatrics hospital. So let's look at FIS data, which is the Children's Hospital Association data set that I'm sure a lot of you are familiar with. And there we decided to look at asthma treatment. And there were 37 hospitals in the data set that had good data that out of the 41 at the time, or out of the 40 that we had data available on, there were 37 that had reasonable cost data that wasn't too crazy because we're going to look at costs. And let me just set this up. First, this is the same kind of table that I showed earlier for that Hospital A and in the Medicare example. Now we're going to look at two of these similar tables, One is a random sample from these hospitals. So there's 37 hospitals, and we randomly sample asthma patients to make a template, but it's a random sample of their patients. And this is the template match sample. If you look at the random sample, this is the median, for example, age, and then sex, and Medicaid status we'll look at for a minute. In the random sample, looking across variables, what you'll find is big differences across the children's hospitals. So the children's hospitals, seeing asthma, they see different kinds of asthma patients at the children's hospitals, even though they're all highly technical, sophisticated hospitals. And you can see big differences across the variables. For example, and as I said, let's look at Medicaid status, highly different. The lower eighth had 41% Medicaid patients, the upper eighth 68%, and that was highly significant. Now let's look at the template sample. So what we did was form a representative asthma template and stamp it out on all the phys hospitals. And now what we see is no difference in any of the variables for these patients in the template at the hospitals. The ages had no difference. The Medicaid status, the lower eighth was 60.5, the upper eighth was 63.8 versus 41 and 68. So what I'm trying to convey is that you're seeing something you haven't seen before, which is you're matching patients, and now you can compare hospitals in a direct way through the advance of multivariate matching. Now let's ask, well, is there a difference in outcomes? Well, in the random sample, there was a difference in outcomes. Let's look at cost. Cost was significantly different across the hospitals. Cost meaning resource utilization. And length of stay was very different, and ICU utilization was very different. Now, it's also very different in the match sample, but that's the surprising thing. If the patients look the same, but the outcomes are very different or the processes are very different, then we could ask ourselves, is somebody doing the right thing and someone doing the wrong thing, and why is that occurring? And this is just a little example. Each letter, and there's a reason why they have different colors, but each letter represents a hospital. On the in the children's hospital in phys. On the x-axis is kind of a length of stay measure. On the y-axis is cost. And what you can see is big variation in cost. Now, this is the average cost of the patient in the template, $3,000 up to $7,000. And you can see that hospitals varied tremendously on cost, even though they were the same patients that were copied across the hospitals. If you look at the ICU utilization, the light shade is low utilization, and then it's a gradual increase to the dark shade. So the lowest shading was 3.3% of the patients in their template went to the ICU. The highest shading was 35% of patients went to the ICU. And one thing you can see is that there is a relationship between length of stay and cost, but in terms of ICU utilization, you're not necessarily a lower cost hospital because you don't use the ICU. You could use the ICU very little and still be expensive. You can use the ICU a lot and still be cheap. And you can see from the shading here, this would be someone who uses the ICU a lot because it's a darker color, and they're fairly low in terms of cost and length of stay. And here's another hospital that uses the ICU a lot, and they're a high cost, long length of stay, and you have everything in between. So one lesson here is you can't feel too good about the fact that you use the ICU less if your outcomes are similar. If that is a definite marker for less cost, it isn't necessarily. Okay, so in summary for template matching, we're saying, well, it's a good idea because, first of all, it's a fair exam. Everybody gets the same question, the same 300 patients across their hospitals. They're all evaluated on the same 300 patients. So it's a fair test. And secondly, it's a form of this direct standardization. And thirdly, and I think it's an effective way to benchmark because now you know how you did with the same patients that someone else did. You can look at sections of that template and see where you're strong and where you're weak, and I'll get into that a little bit later on. Okay, so the next technique that I want to show you is called hospital-specific template matching. And it's a form of what I call indirect standardization, and I'll show you why in a second. So the chief medical officer might wish to know how their hospital is handling their patients compared to how other peer hospitals would perform with the same hospital's patients. Why is that? Well, you could say, look, you made a template, and we didn't do so well. But that's because the template that you constructed didn't reflect our strengths. We see different kinds of patients, and even though we could fit the template, and it was a reasonable match and we could fit the template, it really didn't tap into why we are as good as we say we are. So we go back to the chief medical officer or the chief quality officer and say, fine, we're going to make a boutique template just for you. We're going to take your patients, construct a template, and then we're going to stamp this boutique template out on all the other hospitals. So now you can see how you did relative to how your patients would have done had they gone elsewhere. So that's called hospital-specific template matching. It's the same picture, but now this template was constructed in a boutique manner specifically for you, your hospital, and now you can find the hospitals that match to you. Now, there's going to be less of them because your hospital might see a unique mix. But generally speaking, you'll find plenty of other hospitals that can match your template. And now you want to know how your patients would have done had they gone elsewhere. And now I'm going to go back to that same hospital that I showed you, Hospital A, that didn't look so good with the template. So maybe their chief quality officer would say, yeah, but if you made a boutique template, we'd look better. So here's the results for Hospital A. We can look to see they were 98th percentile in terms of badness, in terms of mortality. Now they're 97th percentile. So they have the same problem in terms of 30-day mortality. What we can show is the templates look very similar across the hospitals, but this hospital, even when making its own boutique template, still looked bad. They still had a problem. We have to figure out why it is that they have a problem. Okay, so that's the second method. And the third method says, all right, forget the template. I want to look at all my patients. I want to see how I'm doing relative to other hospitals on everybody or in everybody in a certain service. And so we developed a method called Indirect Standardization Matching. This is coming out sometime in the next few months in health services research. So this is what I'm saying. There's a situation where the CMO wants to evaluate a large number of patients at their hospital and where the type of patients in the hospital might be unusual, so they want to use all the patients. But in any way, for whatever reason, they want to look at a larger sample of their hospital's patients. And so what we say is, okay, let's do this with what we call indirect standardization matching. Let's find 10 copies out there in the database from all the other hospitals. For each patient at your hospital, let's find 10 duplicates. And now let's see how you did versus those 10. So the hospital is not going to be compared to other hospitals. We no longer have precise rankings and directly standardized rankings. But we ask whether their patients are experiencing better or worse outcomes than they would have experienced at other hospitals that typically see patients like them. And this is the picture. So we now have, in this case, we went back to Hospital A in the Medicare database. They had 1,773 orthopedics and general surgery patients. And what we did was we went out to 3 states of data in Medicare, and we copied for every patient in the template, meaning every patient in their service for general surgery and orthopedics. We found 10 close matches. And we found those matches throughout the Medicare database. And then we would ask, well, how did this hospital do? So if we now look at, and by the way, we would exact match on the procedure and then closely match as best we can for other characteristics. This is the probability of dying by various risk models that were not based on the same data that we used to be analyzing this hospital. And we can see that the probability of dying is very similar. There were no differences, and the matches were very close between the hospital's patients and the 10 copies that we would find of each and every patient at that hospital. And so they have very, very similar patients. And if you look at how that hospital did, we can see they're not doing so well. Their death rate was 4%, and the match controls had a 2.8% death rate. The odds of dying at that hospital versus if you would have gone elsewhere with closely matched patients that other places had seen was 50% higher. Complication rates were actually lower, failure to rescue rates were higher. That's the probability of dying after a complication. So this gives you an idea that you can kind of use this matching to look at quality, be it if you have a template or not a template. You can actually just do this with direct matching with a good matching ratio, 10 to 1 in this case. Okay, so what can you do with this matching to give you a better insight as to how your hospital is doing? So let me walk you through this graph. This is just the way we conceptualize this. There's a thing we're calling specific advantage and then outcome synergy. The x-axis is the average risk based on some external model of the patients in a matched pair. So we're going to look at a hospital and all of its matched pairs with all those controls. And for each set, there's a predicted risk. It could be the risk of dying. It could be the risk of getting an infection. It could be the risk of staying a long time in the hospital. But what we're going to say is there's an average risk for each matched set. And then we're going to look at the difference in outcomes between the focal hospital, hospital A, or whatever hospital you're interested in, and its matched controls. So if this was mortality, for example, for a point on this graph, if your mortality for your patients were the same as the controls that were found for you, then you would have a zero difference between yourself and the controls. So a typical hospital that was doing exactly the same as every other hospital in the data set in the country and FIS would be a line going this way at any risk for their patients on entering the hospital, their predicted risk. For whatever risk they had, they were average. That would be the dark horizontal line. Now, suppose you're a hospital that's hospital A. Hospital A is always, let's say, 5% more. Let's suppose this was death or it could be cost. Hospital A always is worse than average. Average would be here. Hospital A is always worse than average for every pair, for every set that we have. So it could be a set of, again, 11 patients, in the example I gave before for indirect standardization matching, one patient at the hospital matched to 10 patients elsewhere. Or you could be hospital B. You're always cheaper, or you always have lower mortality than the matched controls. And we would say that hospital A has a specific advantage over hospital B, clearly because overall risk, they have lower death or lower cost than the same matched pairs at the other hospital. All right? Or you could have a situation like in this curve. We call this a synergy because we don't have parallel, these aren't parallel lines. This is a hospital, and you could say, well, at low-risk patients, at this point P, low risk, this hospital is very cheap or has very low mortality compared to all the other hospitals for those kinds of patients. But at high risk, they don't do so well. And this is a hospital that has exactly the opposite issue. They don't do so well for the low-risk patients. They're worse than average for low risk, but they get better as the patients get sicker. You can imagine this one might be, say, a teaching hospital and this is cost. You could say, well, they're expensive for the easy ones, but they're cheaper because they can't do a better job for the very difficult patients. All right, so this is going back to hospital A again. And if you look at hospital A and you kind of ask yourself, how did they do? You can see where their problem is. The red curve represents general surgical patients, and the green is orthopedics. And if we look at 30-day mortality, this is in-hospital plus 30 days, so it's 30-day mortality. What we see is that for general surgery, they start out doing kind of average, but as the risk goes up, and this is the distribution of risk, so most of the patients are between this is the 25th to the 75th percentile in terms of risk, but as the risk goes up, they do worse. So they have to analyze why it is that they're doing worse on this subset. For orthopedics patients, it's pretty flat. They're good, they do better than average, and it isn't until they're basically there isn't any synergy here. Their problem is in general surgery, and in particular, they have a problem with the higher risk patients. So let's look at FIS hospitals. So I showed you that example about asthma in FIS, and I'm just giving you 4 examples from the 37 where we looked at, these are asthma admissions. Each one of these, hospital Delta, L, C, and N, are different phys hospitals. I don't know the names of these hospitals. Although I could, but I generally don't like to know the names so that no one thinks I'm talking about them when I'm presenting. So this is a hospital that is always more expensive no matter what the risk for their asthma patients. This is a hospital that generally is less expensive than the rest of the hospitals in phys. Each point is one hospital minus the 36 other hospitals in phys. So again, so if you're up here, you're more expensive than on average than the 36 other hospitals, and if you're down here, you're less expensive. Some hospitals are cheap for easy patients, but then get very expensive or more expensive for hard patients. And others, we all like to think this was us, you know, we're better than average always, and we start out being cheap, but then we, even with the very hard patients, we're so good that we save a lot more money than the other hospitals treating those same patients. All right, so the last thing I want to talk about is how do you look at value with this framework. And in this study that's coming out soon, we looked at magnet hospitals, hospitals with good nursing environments, and compared it to hospitals with poor nursing environments, and we also threw in the criteria that was good staffing levels, better than average versus worse than average. So the cases in this case are going to be hospitals that are magnet certified, meaning good nursing environments with better than average nurse-to-bed ratio. And we're going to compare that to hospitals that had below average nurse-to-bed ratios and were not certified. So value, which I don't like to look at, is often quality over cost or cost over quality. The reason why I don't like value is that I always am worried about the race to the bottom. I'm always worried that what we're going to see is that you can get the same value with high quality and high cost as you can with low quality and low cost. That worries me, and so I'm always objecting to insurance companies that want to talk about value. I want to make sure that they report that you have to look at the Q and you have to look at the C separately before you can talk about value. But other people might not agree, but I think it's important to always disaggregate the things that go into value. So let's look at this question about better nursing environments and more nurses versus less. These are going to be, this is a data set. I won't go through all the details because I'm kind of short on time, but these are matched pairs. We found 25,000 general surgery and orthopedics patients at these two groups of hospitals. So we have 25,000 pairs of patients. They have various risks. And then we're going to subtract, in this case, we're subtracting the death rate at the magnet hospitals minus the death rate at the non-magnet hospitals. So better nursing minus good nursing. And what we find is the mortality rates at the magnet hospitals are lower, and as the patients get sicker, the mortality rates continue to get lower and at a greater rate than their controls at the non-magnet hospitals. So the magnet hospitals are good for you, especially when you're sick. And if we look at cost, you can do cost in two ways, and we kind of had debates with the reviewers from JAMA surgery about this. So let me start here. This is a cost which says, for a given risk of patient, what's the difference in cost between the magnet and the non-magnet, where we don't put in the extra nursing costs for a high nurse-to-bed ratio. So we just say, assuming that the nursing costs in terms of the amount of labor purchased was the same between the hospitals, what would happen in terms of the cost that the patients accrued in terms of resources, bills that came from Medicare. And what we find is it's a lot cheaper at magnet hospitals. They're below this horizontal line. As the patients get sicker, they're generally dropping in cost, although it begins to level out and it actually go up a little bit. But the point is that you do save money if you are talking about the costs that are expended on the patients. If you then put back in the costs of the extra nurses to get you to those higher nurse-to-bed levels, what you get is that there isn't as much of a difference. right? But that's the cost of the extra nurses, but the extra nurses bought you something. You saved a lot of money in other respects. So the last slide I want to show you is just showing you a value plot using matching in the same framework. And so let's start on this side where we don't put in the extra costs of nurses. Each bubble, there's different colors. There's a central bubble, which is all 25,000 patients. And then as you go from the smaller bubbles to the larger, you're talking about groups of about 5,000 patients, it's hard to see here, of the lowest risk in the green, then the next lowest, then the next lowest, until the 5 is the highest risk. So 5 groups of 5,000 from the lowest risk to the highest risk. And what you see is that the mortality, I'm sorry, let me set up the axes. So the horizontal line here, if we look at and we're looking at the vertical axis, this is the difference in quality, or in this case, mortality. But now we're going to make it so that it's good to be in the upper right-hand side for the better nursing environments. So we're subtracting the bad nursing environments from the good nursing environments. So if the bad nursing environments had a higher mortality than the good nursing environments, you would be above the line. Good for the nursing and bad for the hospitals that didn't have good nursing. So you'd like to be up here if you were in favor of magnet hospitals. And then in terms of cost, what we're saying is if you're, this is the central point for cost. This is the 0 point, which says, I'll stay with this graph, says no difference in cost. If I'm to the right, it says that the non-magnet hospitals are more expensive than the magnet hospitals. All right, so up here, all these circles say that I'm doing better with magnet hospitals and I'm cheaper. The sides of these circles represent the confidence bands. So I can say that for all of these, I'm not touching, I'm hardly touching the cost line. Here, I'm just barely touching it. I am significantly cheaper, and also once I get to a certain risk, the low-risk patients, there's still some statistical lack of significance, but as I get to higher risk, I'm clearly better in terms of mortality. And this circle is the overall risk and cost. So this is a joint confidence interval with cost and risk, and it says there's a slam dunk for value. Because I'm cheaper, I'm this direction, and I'm lower mortality, I'm above the line. And if I go to putting back in the extra cost of extra nurses, which could have affected this problem. The economists debate this in our group and with the reviewers because if we put in the extra cost of nursing, there's lots of other costs we could have put in. If we kept it clean, it would just have been patient costs that are being accrued. That would be this graph. If we put in and penalize the magnet hospitals because they hire more nurses, then that's this graph. And what we see is the outcomes won't change. So all these points going on the height, they're all going to be the same. They're all having the advantage in terms of mortality, but now the costs are shifted. But look at what the costs are. You gain about a 1 to 2 percentage point increase in survival, and what you give up is most of the time a cost that is almost the same between the two groups, possibly here $1,000 difference, $2,000 difference at most for the highest risk patients, but you bought a lot. So we would claim, and what we say in the paper is, well, this is clearly value, but so is this, because you paid a little bit more, but you got a tremendous improvement in mortality for these general surgery and orthopedics patients. So what I've tried to do today is to show you that multivariate matching allows for a transparent and clinically credible approach to comparing cost, quality, and value. I've tried to make that argument. And that the 4 approaches that I've showed are only strengthened by better data. The better data we get, the better and more convincing we can be in terms of saying these patients are similar, and then we look to see if the outcomes were different. So let me stop there and see if there were any questions. Yes. You have to shout. Sorry.
Question. I will assume for a moment that your case report at the beginning, 30.
Assuming that your case report at the beginning, 38 or 32, was not a hypothetical.
No, it was hypothetical.
It was hypothetical?
Yeah, but I mean, I can say I remember when Penn had a problem with their bypass surgery, and President Clinton, in his State of the Union address, said he singled out Penn as being the most expensive and also having the worst. That was us. And I was brought into that board meeting to try to see what went on. And a lot of shakeups occurred from that. Yeah.
But was the methodology ever applied even after the fact there to see if it was that was affected?
Oh, you mean have I gone back and done this?
Yeah.
No, I haven't, but that'd be a fun thing to do. Yeah.
Thank you.
This is great. One thing that bothers me is that we still focus so much. I do cardiac intensive care. We still focus so much on mortality as our primary outcome measure. With these new matching, the new matching methodologies that you've described, are you trying to make a push, or is there going to be a push toward utilizing other endpoints and other markers for quality? Because mortality is such a rare event now, and quite frankly, a very poor marker of quality, and it shouldn't be what we tout ourselves
with. Right. So I mean, with a lot of the pediatric examples, we don't use mortality. The nice thing about matching is you don't look at the outcomes. You do the matches, and you get the closely matched pairs. And then you can look at any outcomes you want once you're done with the matching. So mortality is rarely something that we look at across phys hospitals because the mortality rate is low. But we can look at other variables. And we're also doing this with MAX data, national Medicaid data, and we're doing it with Medicare data. So mortality is just one out of any of the variables you can look at in terms of outcomes. I think people in the adult world like to look at mortality, but you're right. But then again, if you look at ICU care, you might still want to look at mortality. But in no way is this, is there anything special about mortality in what we're doing? Yes.
Oh. I get to take over.
Sure.
Big question. My concern is these big databases and how valuable the data is. We use the FIS database a lot, and we've had a lot of problems with it. Pulling out diagnoses, we find it to be, really the data is not good. This is why we started a Children's Hospital neonatal database, so we could get our own data. We have been able to match up with FIS to look at cost, but looking at outcome with FIS data makes me very, very concerned. When you pull the number of diaphragmatic hernias at one of my colleagues' hospital that has a huge population, they only pull about half of the kids using that diagnosis to pull out. So I'm a little worried about using some of these big databases and what the quality of that database is.
Well, that's a great point. And, you know, we're always worried about data quality. And with FIS, yeah, we spend a lot of time making sure that what we're measuring seems reasonable. So that includes the cost data. We don't really have the outcomes that I mentioned here. We were just looking at cost, length of stay, something that they can measure fairly well, and ICU, you know when someone went to the ICU. But you're right that you have to be very careful, like for any data set, about the data that you're analyzing to make sure that it's valid. So I mean, I'm all in favor of checking and double checking and doing validation to make sure that what you're saying is reasonable given the data that you're looking at.
So given the hour, I want to thank Jeff for a fabulous talk, giving us some real insight into how we measure what we do. And it's sort of obvious that from there we can then think about how we do it better. There is going to be a roundtable discussion in the medical education suite. Several of our leaders will be there to sort of present cases from children. So Billy, some of the issues that are here, and get Jeff to comment in a more informal session. It's from 9:30 to 11 o'clock. It's been fabulous. Thank you very much. And Grand Rounds is closed. Thanks.